Early? Yeah. Okay, I'll do that. So I'm going to talk about a language to rule them all. You can imagine which one is that already. Okay. What I'm going to look for is, what I'm going to look at is all cool things that new languages do. Because languages nowadays are very different to how they were in the 20th century. So there are lots of new languages. They're coming out every day. All languages are also getting new features all the time. So I'm going to look at that to see how they do stuff, right? First thing is Unicode. It's something that we didn't have in the 90s with C or C++, but it's everywhere now. You need it for all kinds of things. Like for instance, here you see that you got stuff in 3 different languages. This is actually a picture I took right there in the Mount of Olives. You also have to create programs and applications all over the world, so you will eventually need to deal with all kinds of alphabets and everything. And Unicode is important. It's really important. It's really something that you have to take into account. It's not only for getting that kind of applications, but also for extracting information out of databases, scraping, anything like that. So many languages use already Unicode, not only as a string, but also as identifiers, and also as part of regular expressions. For instance, you look here, this is a function in JavaScript, in plain JavaScript. You see that you can write the identifier of the function in Greek characters. So something like is Hellenica. So you get the input, and then you apply a regular expression, and you say that you check that it's actually written in a script that's Greek. You got this U here. What does it mean? That's Unicode. So JavaScript is able to handle Unicode, but it's not the default. But still it can do it, right? So it returns something, and then it returns a test, and then you check if the letter P is in Greek, and you can do that. So that's something that many languages can do. JavaScript can do it, Python 3 can do it, and many others can, right? So it's not something that, it's not ubiquitous. What? Say that? Ubiquitous. But it's pretty much everywhere, right? So you can use, all kinds of things. Just check out that we can use this accent here, which is kind of nice. But anyway, it's something that many languages have, and it's cool to have, right? Second thing, lambdas. Lambdas are very, very important. Using a lambda means that you have, you can treat functions, you can handle functions in pretty much the same way that you would use any other data. So you can have some variable that contains a function, you can have a variable that contains a hash, you can have a variable that contains anything else, and they will be dealt with exactly in the same way. And you can also use lambdas. You can create a function on the fly, and you can put it anywhere that you could put any other kind of data. For instance, they are sometimes called lambdas. Python, for instance, has them. We'll get back to this later on. But you see that you can just say, we have a lambda here. These are the 2 arguments that we are going to use. And then you have the colon, and here's the definition of the lambda. Definition of the lambda is right up to here. And this is something that you are giving reduce. So reduce needs a lambda, then input, and then the initial function, right? So it's going to apply this function to the initial value, which is 1, 1. It's going to generate an array with a Fibonacci sequence, and then here it's going to print 12, right? Python is not exactly a functional language. Actually, Guido van Rossum is known to be pretty much against anything that's functional, but still, they kind of said, we need to do this, right? We need to have lambdas, we need to have first-class functions, and you find them everywhere. I think that Java has them from Java 7, maybe, or 8. Yeah, C++ has them. So you can define C++ function on the fly. So they are pretty much everywhere, but they are very useful if you want to have some kind of reactive functional programming, you need them, right? Something else, immutability. Mutability means that you are able to define some functions or anything, actually any kind of data, that's not going to change. So that means that you can, you're going to use it in data structures that are going to be high performance because you know that they are not going to change. So you have this data structure and it's not going to change overall the lifetime of this data structure. So it means that you will need to apply functions to that. Once again, this is kind of a functional language. I think that functional languages are kind of the language of the 21st century, same as probably object-oriented languages were the languages of the last decade of the last century. What's immutable can be changed, obviously. So it's kind of a promise. You say this is not going to change. So you need to apply stuff to it. You need to map it to some other values. And you can use it in Scala, for instance. You just say this is a val. This value is not going to change. There are several ways of defining variables in Scala. You can define them with val, which is immutable, with var, which is mutable. But you can also use them in closure. I say it's all as a loop. Actually, what's behind it is an actual magnetic loop, which was a kind of memory that was used in the 40s and 50s. So loops are going to be kind of obsoleted because with this kind of thing, you are not going to use loops. Why? Because you are going to apply a function to it, and then it's going to be another function. You are going to apply map, reduce, or you are going to apply some kind of recursive function, just like this one. This is written in closure. It's counting down to 0, right? So instead of creating a loop, what it's doing, it's calling itself. So that all the time, you know that this variable n is not going to change. You're going to create it as an argument for the next iteration, for the next recursion, and then eventually you're going to close the loop and it's going to print. Closure is kind of an old language, but still it's got this kind of immutable arguments. This also happens in many languages. Some of them have arguments that you pass to function. They are immutable by default. So you need to say, actually, if you want to change them, you have to tell them that they're going to be run and write. So this is something that happens all the time. Yeah. Closure has also got some variables that you can define that are actually immutable. You can't change them at all. Something else, gradual typing. Gradual typing is a very nice thing. It's static typing and also dynamic typing at the same time, so that you can create something that's a variable, and you don't say that variable is going to be anything at all. So in this case, you say that it's static, so you say that second needle is going to be a number, it's going to be 3, right? But you can also say, no, I'm going to have this variable, which is, I'm going to call it first needle, it's going to be a string. And then if you assign another value, like a number or a function or whatever, it's going to change. So in gradual typing, you have both kind of things. You have static typing, which is going to be checked in compile time, and you also have dynamic typing, because you can assign any kind of value to a variable. You can do that in TypeScript. TypeScript is like the next JavaScript. JavaScript is the next Python, and Python was the next Perl, or stuff like that. Anyway, so you can use something like that. Here, we have both kind of variables. We have this first needle, which is a dynamic variable. We have second needle, which is statically defined as a number. You know that second needle is always going to be a number. You know that first needle can be anything at all. So you could handle it to here, and you can actually use it anywhere, right? So here, actually, this one also have a gradual type. You are telling this function that it's going to get 2 arguments. You are not telling it in advance what kind of types they are going to have. By the way, what is this? It's a lambda. So you see that lambdas are pretty much everywhere, right? I have used it here purposefully, so I wanted to show you that you can use lambdas here. Of course, you can use them anywhere. Funny thing about TypeScript is that you actually use the same kind of keyword for functions that you define statically and this kind of lambdas. It's not the same in Python. But in many languages, it's exactly the same. You say, I'm going to define a function, I'm going to do it this way, pretty much independently of whether I do it as part of a statement or as part of a static definition anywhere. You see that, I mean, TypeScript is quite popular. It was created by Microsoft, actually, initially, and it has become like kind of the standard nowadays for JavaScript, because JavaScript doesn't have this kind of gradual typing, unless the last version has, but TypeScript has got this gradual typing, which allows you, if you got types, you can create good, I mean, it scales up to big applications, right? Postmodern assignment. Postmodern assignment means that you can destructure arguments, right? So that means that you can have some arguments on the right-hand side, or when you are calling a function, and then that function is going to take care of extracting stuff from those arguments automatically, so that you can assign many variables on the right-hand side to many other variables on the left-hand side, and those variables are going to be. So I'm off frame. I'm sorry. I like to move a lot. Anyway, so that means that you're going to have single statement assignment. That's pretty practical because you see exactly what you are doing. It's not like you have to use a temporal variable somewhere to hold something where you are swapping things. For instance, you can assign an array to 2 variables, things like that. It's quite practical. It's quite easy. It allows you to easily see what's happening on your program. And it's also type safe. That's a good thing about that. So you say that if you have an array, the first element of an array is a number, the second element of an array is a string, you can assign it to 2 statically typed variables. One of them is a string, another one is a number. So you don't have to go on, worrying about what is really the type of this first argument, the second argument. So you have type safety, and you have also single line assignment. Very practical, very nice. We're going to do it in Kotlin. You know Derrida? Derrida is a postmodern philosopher. He was the one that proposed deconstruction as a methodology for analyzing speech or for analyzing text or anything like that. So this is Derrida in Kotlin, because we are deconstructing the argument. Kotlin is a very, I would say, popular language. It's functional. It was proposed initially by Google. It's theoretically going to be the next Java, because it's going to be used to create applications for mobile phones and things like that. So it's an interesting language. It's very interesting. But it's got this thing. It's got this deconstruction thing. We create this function, which is shared. And once again, this is what? It's another lambda. We have lambdas everywhere. They are pretty much over the place. If it's functional, it's got lambdas, right? So what we're going to do here is basically we are returning a result. You see that the result is this thing. The result is a data structure that's got an integer and a Boolean. Kotlin is very, very good in the sense that you can automatically, you are returning a result, which is this kind of data structure, and you can automatically assign it to 2 variables. One of them is going to be an integer, and the other one is going to be a string, right? So I don't think this is done exactly in the same way in other places. It's because Kotlin has got this thing where variables in data structure have like 2 names. So they are kind of behaving like a dictionary, but at the same time they are behaving like a positional thing. So that this first thing here is going to be the first variable. This thing here is also defined as a second variable. So this is kind of defined as an array and as a data structure at the same time. This is quite unique to Kotlin, but what's not unique to Kotlin is the fact that you can return a data structure from a function, or you can assign a data structure on the right-hand side, and you can convert it and put it into different variables in the left-hand side, right? Kotlin is also quite fast. I mean, it's a very, I think it's a nice language. So it's becoming quite popular nowadays. Then you have pattern matching for complex decisions, like kind of try to avoid if cascades. So if this happens, then do this. Else, if something else happens, then do that. Cascades are dangerous, and they are pretty bad. This is the Skogafoss, Gullfoss waterfall in Iceland. I don't know if you've been there. It's a very nice place to be. And also it was saved from being built into a dam, into a reservoir by a single woman. She single-handedly managed to keep it exactly that way, wild and beautiful. And what?
Now we have less Bitcoin.
Yeah. There's no. I mean, in Iceland they got enough electricity for themselves and for some other.
No use for it, that's why the Bitcoin.
Yeah. That's the thing. So they are building aluminium melters there and everything. But Iceland is a nice place. I don't know if you've been there, but it's a wonderful place. So you can do that in Scala. In Scala, we have this kind of switch or case on steroids, where you have this kind of thing, right? You say if card matches A's, 3, J, Q, K, and then the default value. Once again, this is what? This is another lambda. So we got lambdas again, right? This is the argument to the lambda, and this is what the lambda is going to return. It's using this syntax, which is a fat arrow, which I love. So what it's doing is just checking what is space to that. This will be the points that the Spanish numbering system for cards is using. So if we are playing, different kind of ways of playing cards, you got the days gets 11 points, 3 gets 10, then 2, 3, 4, and then if it's any other card, you get no points at all. So this is actually it's going to give you the points that when you're counting the score you get in a card game, right? And this is written in Scala. The Scala is also I'm not going to say it's a nice language, but it's an academic language. It was created originally not far away from here, in Lausanne. For a long time, it was kind of this academic toy that you use to publish paper, because that's what we do. We publish papers in academia, but then all of a sudden people realize, oh, so this kind of thing is concurrent. It's functional. I can do data science with it, because somebody created this thing called a Spark, and then all of a sudden everybody was learning Scala. Now they are not learning Scala anymore. So Scala was also the next Java. There are so many next Javas that should be extinct by now, but it's not. But now people are going from Scala to some other more complicated things like Agda or Idris, which are purely functional languages. Anyway, it's nice in a way that you can also use it as a scripting languages. It's got a nice tool set that you can use, but you can do this kind of thing. So this is once again this was using pattern matching, right? But then cascades are bad if they are cascades, but they are so beautiful. They are so nice. You can use it to cascade lots of operations and chain them together so that you create some reactive data flow that you get something on the left-hand side, and then at the end you get something that's being processed on the right-hand side. This is also another waterfall in Iceland. It's called Skogafoss. It's very beautiful. I think that the rainbow is actually paid by the government, because it's very hard to go there without a rainbow, but it's absolutely amazing and beautiful. Iceland is also the first one that has certified the death of a glacier. They put a plaque a short time ago saying that this glacier is dead, it's not going to come back. So they're really worried about the environment and things like that. So kudos to this country. It's a small country, but it's a big country. There's not so many people there. It's 350,000 people there. Anyway, you can use Elixir. Elixir, I don't know if you know this language. It's also a pretty new language. It's like, you were talking about Erlang a short time ago, but Erlang is a language that's not for humans. It's like, you need to kind of reach a level of alignment to kind of program with it, because it's quite complicated. The syntax is complicated. And then they say, okay, but this is a nice language. We need to use this runtime to do nice stuff. And then they kind of put together Erlang and Ruby and came up with Elixir. And now Elixir is kind of simpler. But you see that they use this kind of arrowish kind of thing to indicate the data flow. So you got this on the left-hand side. It's going to apply this function, right? Then this function, then this function. So it's going to it's going to filter, then it's going to map it to the power of 2, and then it's going to put them all together. So this is going to get the 100 first numbers, then it's going to take only the odd numbers, the even numbers, and then it's going to elevate them to the power of 2, and then it's going to reduce them by summing them all together, right? What this is, and another lambda, and this is a very nice lambda because it's a abbreviated lambda. You see, you're just saying no, this is a function, and I'm not going to give it a name. I'm not going to use any kind of name for arguments or anything like that. No, the first argument, this is going to be the first argument. This is going to be the second argument. You see, it's very compact. Once you get the hang of it, it's very kind of mathematically oriented. You know that something is going to come in this side and something is going to get out on the other side, and yep.
What do the %1 and %2 refer to actually?
The first and second argument. So this is a function that this means that it's a function, and this means that that function is going to add its first and second argument, and that's it.
And where do the arguments come actually?
Since it's a reduce, so what reduce is going to do, it's going to pick the first element of the array. Okay. That's going to be the first, the &1. Then it's going to add the second element of the array. Then what it's going to do is the result of that function is going to be again the first argument. Then it's going to add the third one, and so on and so forth. So reduce is kind of summing stuff up, taking it from left to right. You see that this put s is from Ruby, so it's you can probably do that in Erlang, but I have no idea how you would do that. But you see that it's it's kind of very powerful and it's kind of nice. Then multiple dispatch. Multiple dispatch is overloading. It's like overloading. What you do is you give the same name to a function, and then you have different implementation for a function depending on the signature of the function, right? The good thing is that you can have kind of high performance because it's easier to match signatures that do an if and say if I do this then this, if I do that then that. No, you just match signatures and say I'm going to apply this function over here, right? You can do that with Julia. Julia is also the next Python. You say yes because it's true. So Julia was also kind of an underground language. It wasn't too popular, but then all of a sudden they produced a version 1, which was I think early this year, and people are warming up to Julia because Julia is concurrent. It's got a very powerful macro facility, so you can do lots of stuff. It's fast, it's compiled, and as soon as it gets some libraries or anything like that, it's going to be very, very popular. It's kind of the thing that people are using now in data science, because in data science you can use R, which totally and absolutely sucks. You can use Python, which sucks a little bit less, but also it's Python. So, but you see that this, for instance, this ampersand over here, it's a macro. So macros are so much integrated into the language that some of the basic things you do there, you do them with macros. Macros are nice in the sense that you're using the same language to generate the structures of the language, but this is kind of a clutch, but still, you see it all the time. It's like Python with ampersands. It's like, no, we're going to have this very simple language with no sigils or anything, And then all of a sudden, no, we are going to use these signals because yes. And so this is basically what it does is it's defining two different kind of enums. One of them is for the suites of the French cards or the one they use in America, and these are the Spanish ones, right? So I define suite with these 4 symbols, and I define palo, which is the equivalent in a Spanish card, bastos, espadas, oros, and copas. And then I define two different two-string operations, one of them for suites, another one for palo, right? So we say, if we get an int and then a suite, I'm going to apply this thing, so just the number and then the suite. If we get this thing, we're going to use, instead of this, we're going to write it down in Spanish. Very simple thing. I don't want to write anything complicated, but just think about more complicated signatures and more complicated, something that you would actually want to improve the performance. And you print a len to a string, you call it with this symbol or this symbol. Just check out that these are symbols. They are not strings. So I have defined the symbols here. So I'm calling it with a symbol because they need to be different types. Enums are types after all. So if this was simply a string, it would be more difficult to do. Probably not impossible. I'm not an expert in Julia, but you could probably do it. But you see that this kind of thing is quite practical. As soon as you got complicated functions that kind of do the same thing, but they apply to different sets of arguments, you are going to need that. They still have the same name, so you understand logically what they are doing. The flow of data is quite clear. This is very nice. So Julia is a nice language. I think it's worthwhile to learn it. Sloths will hurt dear. Lazy evaluation is very nice. It's something that it allows you to work with infinite structures, which are very big structures. You can work with them all the time. You can multiply them or whatever. It's something that gives you a very powerful way to deal with mathematical data structures, but also with other data structures that needn't be mathematical, just difficult to compute, right? We're going to use F#. Ever heard about F#? There's also a language. You heard about that?
Heard.
Yeah. Yeah, it's kind of a small language. It's fully functional. That's because of the F. The sharps comes from, obviously, it's in the C# platform. So it's kind of like Clojure was something that was working actually on Scala and Kotlin. They all work on the JVM, on the Java Virtual Machine. F# works on the I don't know how it's called, the CLI. It's the runtime platform for C#. So it works it was also proposed by Microsoft. It's got very few followers, but the followers are like, very staunch supporters of F#. You see here, this thing, exactly the same syntax. Once again, we are using this kind of cascading functions, and once again, we have lambdas, right? We have this lambda here. We define a function on the fly, which is going to have this. This is called the Horadam sequence. It's kind of a generalized Fibonacci sequence in which instead of adding the first 2 elements, the previous 2 elements, you add the 2 elements, but you multiply them by any arbitrary number. Like in this case, we are using 0.25 and 0.75. So Horadam function sequence, kind of a generalized Fibonacci sequence, right? We are going to apply it to the also the first 2 elements of the sequence are not going to be 1 and 1. They are going to be, by the way, if you don't use 1, 1, it's called, I think, Lucas sequence. So Lucas sequence is a generalized integer Fibonacci sequence. This Horadam is a generalized sequence for any kind of number, like floating point, right? So the good thing about this is that by default, F# is going to be lazy. So if you do this, right, we are just defining a sequence, and then until you tell it to take 15 elements of that sequence, it's not going to compute that. This is a lazy sequence. Everything is lazy. F# is lazy by default. It's not computing anything. Only when you tell it, okay, so we're on the Horadam sequence, and we're going to apply to the first 15 elements. You can use that. That's very efficient in terms of memory, It's very efficient also in terms of computing, because you're not computing what you don't need to compute. You're not computing like the first 100 elements or whatever, only 15. And then, well, you do that, right? So laziness is good. It's always good. And then in the 90s, we had so many, object-oriented programming, inheritance, encapsulation, and all that. But then all of a sudden, people realized that inheriting was much worse than composing. Composing is actually much better. In many cases, what you're actually doing when you are inheriting is you're composing some kind of stuff. So composing is much better, right? And there are many ways of calling those things that you compose. You can call them threads, you can call them mixins, you can call them rows. And the basic idea is that you create semi-objects, not a whole object, but part of an object. You can have in those objects either implementation or just the interface, or both, depends on the language. So you put them together and you create an object by composing, using just composition. We are going to use Rust. Rust is the new C. But actually I think that Go was going to be the new C. So maybe Rust is the new Go, or the other way around. Anyway, Rust was proposed by Mozilla Foundation, and it's a system language. So it emphasizes safety, it should be very safe. And it's kind of funny how it works. You define a card, which is a data structure, then you define a trait, and then what you do is, I'm going to implement this trait for this data structure. So it's not like you are saying, no, this is my object, these are the attributes, these are the methods of the, no. I have this object there, which is very well defined. I have this function over there, and then I'm going to say, this is going to be applied to that data structure. This is not object-oriented at all. It's composable or something like that. And then you can apply that, right? You can say, okay, so we define this object or this data structure, and then you put S to string, because it's very type safe. So you really, this looks like a string, but it's not a string. So you really have to tell it to convert it to a string, then the suite, and then you just do this kind of thing, right? So you could also add some more things, like adding some other stuff to this card, but you kind of compose the methods with the data structure, and then you can compose those data structure into some other, those methods into some other data structure or whatever. This is safe. This is also kind of easy to test. It's very easy, relatively easy to implement. All in all, it's a nice thing, right? And as I said, Rust is also a very interesting language. It's also concurrent, and it's something that's it was proposed not by a big evil company, but it was proposed by Mozilla, which is not evil, I guess. Yeah, this is me. That's my Twitter account. That's my GitHub handle. I got it very early, so I got 2 letters, which is nice. I work with Perl 6, with Camellia or Raku or whatever. I mostly do the documentation, but I also create issues all over the place. So we're talking about what's a killer app for Perl 6. Maybe we don't need a killer app. Maybe there is already a killer app. But I think that learning programming languages is a killer app for Perl 6. I had absolutely no idea of all those things before I set to program them. And I did all of them. So they're right here in my computer. I can show you. But the thing is that all these are in Perl 6. All those concepts, which are modern computer science concepts in programming language, and many more, like concurrency, like many other things, they are all in Perl 6. They are right there. You just learn them, and then they are there. The thing is that it took me a while to program them. So actually the most difficult one was Kotlin, but only because they had changed the kind of how they define the main function from the 0.9 whatever to the 1.0. So I had one version that I installed in my computer, and then nothing worked. But and then I asked in Stack Overflow, and somebody came up and answered pretty fast. As I said, it took me a while because syntax is tricky. So if it's a arrow, whatever, you have to know if it's an arrow, if it's an equal, and then you know, whatever, or if you have to define, you have to print, for instance. Some of them use puts, some of them use println, whatever. You have to learn the syntax. But it's easier to say, how do I this complicated concept like composability in Kotlin or composability in Scala or whatever, that, you know, try to wrap your head around some problem that you want to define in that language. As I said, not terribly difficult. And I had never, well, I had used Python, of course. I had used a little bit of Scala, but I never done anything in Rust, in Elixir, or any other languages. And this was really easy, right? The most difficult part was I had to install a new Emacs mode for every one of them, so that I had all the code everywhere, you know, looking beautiful. Because if it doesn't look beautiful, I can't program. Perl has everything on the kitchen sink. That's maybe a bad thing, but that's maybe a good thing. Maybe that's their killer app. You see Perl 6, and this is my kitchen sink. It's right there. And this is a program that uses every one of the concepts that we haven't seen there, and some of them that we haven't seen. This is called the Collatz conjecture. What I'm doing here is the Collatz conjecture says that if you apply in sequence an operation to a number, you will end up in 1. So what I'm doing here is checking if I get to 1 in 15 numbers. So the conjecture is that every number is going to get to 1 eventually, but that hasn't been proved mathematically. Biggest number so far, I don't remember, it's, you know, billions or trillions or whatever. It's working for every one of them. I'm not going to do that. I could do it with lazy evaluation, but I'm not going to do it. But you see that you have multiple dispatch here, you have lambdas. You have also something that very few languages have, which is this kind of signature where you are checking not only the type of the signature, you are also checking something else about the signature, like checking it in runtime. In this case, I'm checking whether it's divisible by 2 or not. We have lambdas, for instance, here. This is a simple lambda. Do you know what's this?
Unicode?
It's Unicode. Yeah, warm. It's 1001 in Arab digits. There is no language that's able to use Arab digits. No language. None, really, no. You can't do that in any language. So it's you see, it's counting from 1000 to 1, but you know that Arab is written on the other order. So this is a range that goes from 1 to 1000, right? And it's written in the right direction, and also it's using a Unicode property, which is digit. With Perl 6, you can build numbers using real digits. There are only, as far as I remember, 4 alphabets that have the digit property. One of them is Arab, the other one is Latin, another one is Burmese or Balinese or something like that. There are only 4 of them, right? But you can do that in Perl 6. You can't do that in a language. If you put that in a language, say, no, I don't know how to do this. What this is a string. What's this? No, I don't know what's that. You can actually do arithmetic with that kind of thing. You can add that to some other thing, right? Not all numbers have the digit quality. For instance, if you see a 20 in a circle, that's a number. That's not a digit. If you go at 2 in a circle, that's a number. That's not a digit, right? This is the, if I remember correctly, DD property. So that's one of the things that you don't have. You see that I'm using this kind of thing forever. This is a Unicode symbol used as an identifier. I define this function here, right? It's going to be a prefix function, and it's going to be 2 arrows together. This is a single character, and then I'm using it right here. And I'm using my favorite letter, which is the thorn letter, which is Icelandic because I love Iceland. And it's also the letter that goes in the name of Thor, the god of the hammer, marble and everything. So everything is here, it's right there. Some other goodies, for instance, this thing, if you prefix some stuff to a method call, you first check if you can actually call that method on that. And why do I do that? Well, it's funny you ask, because what I do is that I return this number, but then I add a trait in runtime. So this is a number, but I kind of piggyback on that number, and I say this is going to be called. And then here, if it can call that function on the number, it's because it's got this kind of piggybacking thing, that kind of payload, right? So I check the payload. If I don't check the payload, it's going to look like a normal number, right? If I check the payload, which I do here, it's going to have this collapse thing. This is a programming pattern which I really love. And you, as far as I know, I don't know every language in the world, of course, but I don't think that you can do this kind of thing of composability in runtime in any other language. And you see, it's quite, how many lines? It's 12 lines. It's a dozen of lines. And everything is there, right? But it gets better. Sometimes it's faster. This is the initial thing I did with you remember Python, right? So what I did was some very simple Fibonacci sequence, right? So what I was doing is I was generating what was this? Here, right? So what I was generating is a Fibonacci sequence. Here in this case, I was generating it for 12. So I said, let's see if this is faster than Perl 6. I really didn't have I mean, my hopes were not up for Perl 6 because it's not known to be like the fastest thing. So I said, okay, I'm going to put 10,000 here. I'm going to do it for 10,000, 20,000, up to 65,535, right? Which is, so what happens? Yeah, drum roll. You see, this is Python. This is time. It's a logarithmic scale. This is Perl 6. Let's say, okay, 10,000, yeah. 20,000, no problem. 65,000, yeah, it's going to be a bit slower. But Python, it was like, whoa, I can't do this. It was like, the difference was in this case, it was 1.5 seconds to 45 seconds. It's just amazing. And then I put it in Twitter, and I got lots of reactions. I said, yeah, you know what, it's going to be faster if you actually put a function instead of a lambda. They said, yeah, function and lambdas, exactly the same thing. So I wanted to compare implementation to implementation. So in this case, you see a 40% improvement of Perl 6. So of course, you're going to find other areas where it's not going to be so much fast. But anyway, learn Perl 6 to learn every single language in the world. All of them, past, present, or future, or at least the cool ones. You're not going to learn PHP, for instance, or Java. Anyway, so I hope you didn't get asleep. This is a very bad slot for Spaniard like me, because it is a siesta slot. But this is a incredibly beautiful picture from a Spanish surrealist painter. Her name is Angela, and I mean, I just love it. I saw it in the Picasso Museum in Malaga, and I just wanted to show it to you. And she's sleeping under her eggs. Was she dead? Yeah, no, she's not dead. Maybe she's dead. Yeah, it's about, the egg is a symbol of the beginning, and who knows? I mean, it's I just love it. It's wonderful. So, questions, comments, and that's it.
So you're able to count in Arabic numerals.
Yep.
Can you do it in Roman numerals?
You can do it, but Roman numerals don't have that digit thing.
Exactly.
So you can operate with them But the thing is that you know that Roman numerals are not positional,
No.
so so you have to kind of add them together. If you put an M and an I together, that's not going to be 1001, right? So you need to kind of convert them to number, and then convert them back. So the thing is that you're going to say something, Liz?
Yeah, I was going to say somebody actually made a slang Roman,
Ah, right.
that actually does that. So you can use Roman.
Yeah. Okay. Perfect. Yeah. That's another thing with Perl 6. You got slangs, which are mini languages, which you can implement easily within the language, so you can do that kind of thing. Yeah.
Actually, it does work. I just typed Perl 6-E, say, and the Unicode character for the Roman number 12. It printed 12.
The number 12.
But you can mix them together.
Ah, okay.
Ah, yes. I mean, but if you put an X and then an I and then an I.
Yeah, no, the Unicode glue for the Roman number 12. I used that.
Yep. Maybe if you put them together, they are going to generate a normal form, which is a single code point, and it will work. But my point, if it's that needn't necessarily work. If in many cases, if you put a complicated number like X, V, I, whatever, that's not going to work. So you have to add them and then convert them back into. Yeah.
Yeah, and to make a point to the previous slide, you don't have to learn all of the language. Just use Perl. You can actually use a functional language only in Perl 6. You don't have to learn all of them.
That's right. And Unicode.
This sounds like when you learn Perl 6, you have to learn every single language.
No, it's the other way around. If you learn Perl 6, you are at the same time learning every single language.
That's my point. You don't have to.
Yeah, maybe. Yeah.
If you wanted to just object-oriented, you just roughly proceed.
Yeah. Yeah. And also concurrency. I didn't talk about concurrency. I wanted to show some sample of concurrency with Go. Concurrency in Perl 6 is done in the same way as in Go and Julia. They have the same channel-based concurrency, different from Scala, different from Elixir. So, I mean, there are many things. Everything on the 100-year language approach really works. It's really there. So I'm really happy about that. No more questions? No? Okay. Thank you very much.